Okay, Module 1, Tools and Environments, and we're at the end of it. We're going to write a little code. So, all you really need to write Python code is Python installed on your system and a text editor. If you have those two things, you can write whatever you want. Um, However, there are a bunch of software packages and tools out there that help make our life easier when we're writing code. And we're going to use, instead of sort of getting you writing code immediately and then sort of introducing these later, we're going to just jump right in with like the whole shebang. So this is kind of a stack of tools that you might find even a professional development shop using. We're going to talk about Git, GitHub for backing up our code, and version control. The various Python packages that are available to us, build tooling called Poetry, testing framework called PyTest, and then our code editor, we're going to use VS Code. And I'm going to talk a little bit about AI and how to incorporate that into learning how to use Python and also just developing going forward, because I don't think we should shy away from using it. I think it's a great tool, and when used appropriately, it can probably help you learn faster and definitely write code faster. Okay, so the first thing we're going to talk about is Git, which stands for Global Information Tracker. And Git is a flavor of version control software. There are lots of different version control softwares out there. In the old days, there was something called CVS, Subversion, aka SVN, ClearCase, or a bunch of them. Some are free, some aren't. But since I think about 2005, when Git came on the scene, it's basically taken over because it is the best and it's also free. To understand VCS, you need to think about what code actually is. So, code is lots of text files. It could be a single text file, or for very complicated things like the Linux operating system, it can be many tens, if not hundreds of thousands of files. And thousands of people work on some code bases, like, for example, Linux. And you can imagine that emailing files back and forth is not going to work for that. Because most people don't have visibility into what other people are working on the system. You have all kinds of different conflict resolutions where if two people are working on the same file, how do you fix that? So, version control software is software that helps us manage everything. The traditional sort of model of version control software is you have a repository on the network somewhere that is sort of the main warehouse for your code base, and then different developers will check out that code base, work on it, and then check it back into the repository. And if there are conflicts with something someone else worked on at the same time, it will have to be resolved. And sometimes those what are called merge conflicts can be resolved automatically by the version control software. Sometimes they require one of the developers who is doing the push back to the repository to manually intervene. So we're going to use GitHub, the free GitHub service, to host the repository for this class. And we'll talk about that next. But here we have sort of a graphical representation of what might be going on. So you have a code base, there are 3 different developers working on it. The other thing version control software does for you is it tracks all of the changes that are made to your code base. So you have full view of the history of every commit that was made. So think of this as the history tree. So we're just kind of going to use each of these symbols to represent like the state of all of the files in our code base. So here we're at state 1. Say this developer does what's called a git clone, which just means pull the entire code base from the repository down to my local machine. Now they just have those files sitting there on their local machine in their working copy, and let's just say they don't do anything. Now let's say developer 2 does the same thing. They clone that same state. They do some work, so they edit some files, and then they do what's called a git commit, which just on their local machine tells Git about their edits. So on their local machine, Git will record their commits, and in each commit they can add like comments like, oh hey, this is the change I made. So let's say they do a couple of them. Now let's say developer 3 is really active. He does what's called a branch. So he does a git branch. A branch just says, oh hey, take the state of the repository and create kind of a new repository off of it that I can push changes back to, and they won't affect the initial repository until such time as I decide that I want to bring the changes from my branch back into the main line. So this developer is going to do a git branch, and they're going to do a commit, and then they're going to do what's called a push in Git, where they push their committed changes locally back to the remote repository. But since they've branched, it's gone back to their branch, and it doesn't affect the main line that these other 2 developers have. But now let's say that developer 2 here decides to commit their change or push their changes back to the repository. They do that, like increments the copy of the repository. You know, there are a bunch of log statements that'll show what changed from here to here, and you can go back and look at the previous versions of all the files before the update. So they've pushed their changes back. So this main line has advanced. But developer 3 down here, they've also pushed to a branch, and this branch has advanced. At some point, this last developer might decide that they want to bring the changes that they have going in their own branch back into the mainline branch. And so they would do what's called a git merge. And this is the point at which there may be some conflicts that arise. If this developer had made changes to the same files that this developer had made changes to, and Git was not able to automatically merge those changes, it will tell this developer when they do the git merge that, oh hey, here are the conflicts that arise, and line by line this developer will need to go through and fix them. But once everything's merged back in, and we have our mainline branch here now that has all of the changes from both developers. We're going to do what's called a fork, actually, which is a little bit different. So this branch still resides in the same repository that the mainline branch does. But on GitHub has this concept of a fork where, so this class, it exists in a repository on GitHub, and you're going to create an account on GitHub and fork this repository, meaning you're going to then have your own copy of the repository. You can think of this as kind of a version of branching. You can push changes from this repository back to the original repository using what's called a pull request in GitHub. But this just will mean that branches that you create will not be automatically seen by the original repository. It's just kind of your own separate repository. Okay, so that means we should talk about GitHub next. GitHub is a website. It manages Git repositories on the back end. So GitHub and Git they're separate pieces of software, but GitHub uses Git on its servers to manage Git repositories for you, and it provides a bunch of nice user interface things on top of Git that makes Git a lot easier to use. Microsoft bought it at some point. The nice thing is you can have unlimited public repositories, meaning you can register a free account and just create as many public repositories, meaning repositories that anybody on the internet can see for free. If you want to keep some of your code private, they have paid plans starting around $7 a month, which is pretty affordable for what you're getting. GitHub is not the only player in town. There are a bunch of hosted repository services. Not all of them use Git. There's like SourceForge, which is still using Subversion, but I think GitHub's main competition right now is GitLab, so you could also check them out. But for this class, we're going to use GitHub. So when you install Python, it comes with a bunch of Python code that's already written for you called the standard library. And this is a library that has implementations for a bunch of functions and things that lots of different Python programs have to do. So it's like you've been given, you're building a car and you've been given the frame, basically everything but the engine, and you just need to make the engine, and you can rely on what's provided to you in the standard library to provide scaffolding and do a lot of what you might need to do otherwise. So the standard library is pretty well documented on python.org. If we go and look at it, the library does increment with each version of Python. So the latest right now is 3.11, and the documentation is quite extensive, and it's fully searchable. So if we look at it, let's look at string. It's sort of free text format. Once you start coding Python, you'll kind of see how these docs are put together a little better. But usually, if you want to know how some standard library Python thing you're using is working, the standard library documentations, it's a good go-to. You might also just Google or ask an AI. They can sometimes get you to a quicker answer than reading the docs, but the docs are always a fallback if you can't find more quickly the information you're looking for elsewhere. But sometimes the standard library doesn't have the code you need, or it's not enough to accomplish the task you're looking for. But you think to yourself, oh, hey, this is a pretty common thing. I bet somebody else in the world has already run into this problem and solved it for me. And that's when third-party packages come into play. And in Python, third-party packages, they can exist anywhere and you can install them from anywhere. But by far the largest source of them is something called the Python Package Index, or PyPy. PyPy is a website. Python ships. Like when you install Python, it comes with a tool to install packages off of PyPy, and you do that by just running on your terminal pip install, and you pass the package name. And then when you do install something off PyPy, what happens is essentially pip downloads an archive file, a zip file or a tar, and extracts the Python code from that file into a directory called site packages in your local Python installation directory. And once they're there, you're able to import them and use that code in your own project. So if we look at PyPy, it's just a website you can search for things. Let's say, first notice that there are almost 500,000 projects on PyPy right now. And you don't have to have any special permission to upload a project to PyPy. You can create an account, and as long as the name of your project is not taken by someone else, you can just write Python code and upload it. Because of that, there's a lot of garbage on PyPy. But that said, there are also softwares that are insanely popular and have millions of downloads a week just because they're so useful. So, there's a library called Requests that's really popular that people use to do hypertext transfer requests, so like loading websites from Python code. So if you look at a project on PyPy, you'll see a number of things. This is like a README that gives you a quick synopsis of what it is. This is written by the developers. They show you how to install it. And then there's some links to, usually there's like more robust documentation somewhere. There's statistics, like it's connected to GitHub, so you can see, oh wow, there's a lot of people have starred this repository. So you can kind of get a feel on PyPy for how popular something is, and the more popular something is, the more okay you should feel about using it, just because you know that because it's popular, if the people who are currently maintaining it stop maintaining it, there will be a lot of pain felt by other people, and so someone else might pick up the ball and maintain it in the future. You may have noticed that when we were looking at PyPy, that request package had a version identifier attached to it. But let's just go back and look at that again real quick. So, PyPy differs from GitHub. Like you can see, it's connected here to GitHub. Like it's pulling in some information from GitHub, and this requests library. It is hosted on GitHub. So like it exists on GitHub and PyPy. Well, what's the difference between GitHub and PyPy? GitHub is for managing the code base to receive edits and updates from developers as they're working on it. The package index is for releases of that code. So like you see up here, the current version of PyPy is 2.3, or of requests is 2.31.0, released on May 22nd, 2023. One tab in PyPy is a release history, so you can see the release before that was 2.30.0, before that 2.29. So on GitHub, the developers are making a bunch of changes, and between these individual releases, the repository on GitHub might go through a lot of different changes, and GitHub provides a window into all of that. Whereas on PyPy, it's like each time there is a release, we zip up those files and then publish them on PyPy as a release. So we can say we have tested, the developers are making changes, and then they're like, okay, it's time to do another release. We run all our tests on it, we know it's good, we package that code up, upload it to PyPy, and we tell the world, okay, we bless this version of our code for use. And so for development, people are gonna be checking out code from GitHub, but operationally, when you're running code on systems or you're pulling in third-party packages, usually you're going to be pulling it from PyPy, and you're going to be pulling a blessed version. And packages on PyPy mostly use a versioning scheme that has 3 numbers separated by dots. The first number here, going from right to left, is the most minor version number, and usually this is incremented for bug fixes. The second number is sort of the middle version number. Usually this is incremented if there are no breaking changes on the code, meaning like if you're using a library, you are using an interface that library gives you, and if that library changes that interface, then the code that you have written that uses that library will break. So if a breaking change is made by the library maintainers, they'll usually increment this version number. So let's say request released library version 3. That's a cue to everyone who's using it that, oh, there might be some breaking changes that will break my code if I upgrade from version 2 to 3. So I should be careful to not do that just willy-nilly on a production system that's running code. This middle version number is usually for updates that are functionality updates that don't break code that is using the library, so we can be assured that the interface to the library has not changed if we see a middle version number update. But there is maybe more functionality that we might want to take advantage of there. So go in this direction, left to right. The major version number, this is breaking changes. We can't be assured that our code that uses requests will work from version 2 to 3. Middle version number is new functionality release. And then the last one is, this is a bug fix release. The interface has not changed at all. There's no new functionality. It's just we've actually fixed a problem with the library. So you might be thinking, Python sounds pretty great. There's all this code that is already written for me that I can just bring in and do a bunch of stuff for me. And that is absolutely true. And that's one of the reasons it's so popular. But there is no free lunch. And this does introduce a problem. And that problem has a name. And that name is dependency hell. So, for example, say you're working on your laptop, you have 2 different Python projects that you're working on that do different things. You share a Python installation, like you have one installation of Python on your laptop. Both of these projects are using it. Now, you might bring in different dependencies for each of these projects from PyPy. However, sometimes dependencies conflict with each other. Like, for example, your dependencies also have dependencies. So when you install a package from PyPy, it doesn't just install that package you installed, it installs all of the other packages that package depends on, so on and so forth, until you have pulled an entire graph of dependencies. Now, somewhere far up the line, one of those dependencies might break if some other dependency is not a specific version number. And let's say your other project requires a dependency that has a different version number. So when you install these, you're now going to start getting errors that might be hard to track down, because the dependency environments of your 2 different projects are stepping on each other. Sometimes these problems will manifest when you try to install the packages. Sometimes they will manifest when you run your code, and they can be somewhat unpredictable. So there is a solution to this, and it is called Python virtual environments. And the theory behind Python virtual environments is, oh, hey, let's just create 2 completely separate dependency environments for your different projects that you're working on. So what actually is a Python virtual environment? Simply put, it's a directory. So when you install Python, and if you're using PyEnv, like we recommended, you might have a .pyenv directory in your home directory and all of the different Python versions, mainline versions that you have installed. So I've been using 3.11.4, it's the most recent version recently. If you go and peek inside this directory, this is what Python looks like when you've installed it. I mean, I've removed a few things here just for simplicity, but these are the major bits. You've got a bin directory that gets added to your path, so you see that pip, the thing we install packages from PyPy, is available here, as well as Python. Like when we type Python on our command prompt, this is the executable that we're calling. It's got some include files. These are the C headers, like Python is written in C. These are the C headers that are needed so other C programs, if they want to build against Python and link against Python, they need these, but we don't have to worry about these. When we install, and then there's down at the bottom here, we've got some manual pages. There's an old terminal documentation system called man that these are for. We don't really have to think about these. The directory that we're interested in is under lib. So if you remember, our PyPy packages get installed in a directory called site packages under lib. So we're just dumping, like when we installed requests, if we look at it, there'll be two directories that get installed. There's this dist info. This just has some meta information about the installation of requests, and then the actual Python code. So this is a directory. If we looked in here, we would see the actual Python code that implements the requests library. So when we do a pip install, we get requests, and request depends on URL lib3, so we also get that one. So now let's say I have a project. We're going to call it project 1, and I can't use the same request that is installed on my system Python 3.11.4 that I want to use, but I still want to use this main Python installation 3.11.4. I can create a virtual environment, and I do that. There's a command I can run, python-m venv, and then I can give it a name. And so when I do that, it creates a directory. If I ran that from my home directory, it would create the project 1 directory in my home directory. And if we look at this directory, it looks very similar to our Python installation directory. There's a few more things in bin, namely this activate script. But we see that Python here, it actually links back to the same Python that is in our main Python installation directory. We also have a lib, and in lib we have site packages. So after I create this virtual environment, I can run this other command, source one of the activate scripts. So this source just executes this activate script that basically just tells my terminal, oh hey, I'm going to be using this Python virtual environment. And after I've activated the virtual environment, when I run pip install to get libraries off of PyPy, they will now be installed into this virtual environment. So I can then go and install a specific version of requests. Let's say I want to pin to 2.28.2. So when I run that, it'll install 2.28.2 in my virtual environment. So whenever this virtual environment is activated, anything that is in its site packages directory is going to override anything that is in my main Python's site packages directory. So that allows us to have different versions of dependencies for this specific Python virtual environment. And then when I go to code project 1, anytime I want to run my project, I just need to make sure that I'm using the correct Python virtual environment. And to do that, I just need to run this activate script. So you might be thinking that it's kind of a lot to keep track of. You got all of these dependencies to pull in for your code. You've got virtual environments. You've got the package repository. It's sort of a lot to keep track of, and you're right, it is. But because everybody in the world has these same problems, people have tried to build solutions for all of us. And there are a bunch of different solutions that fall into this broad category called build tools that try to make using all of these different things easier. And recently, Python standardized on a certain kind of configuration file called a TOML file. TOML. TOML's just it's a specific kind of markup language that's pretty easy to read, and the format is called PyProject, and You can record a bunch of things in this file, including dependencies and the name of your package and all of these different things. And build tools will be able to read this file and do things for you. Do things like package up your project and post it to PyPy, or run tests on your project, or track the dependencies and install the dependencies for your project. And we're going to use a build tool in this class, and that build tool is called Poetry. There are a bunch of different tools out there. I'm partial to Poetry. I think it's the most complete. It's robust. I use it in my job, and it can really do a lot for you. So what can it do for you? First and foremost, it will automatically create virtual environments for your project. So if you check your project out off of GitHub and then you clone it on your local laptop, Poetry will create a virtual environment that your project will sort of by default run in. And so you now know that the dependencies you're installing for your project aren't going to step on any other projects you have going on your machine. You can add dependencies with Poetry. So instead of saying pip install requests, you would say Poetry add requests or Poetry add URL lib. You would add dependencies this way, and this automatically updates that PyProject TOML file. It records that dependency in that file. And then to install all of the dependencies, you would just do Poetry install. Now, this is helpful because someone else who wants to work on your project or run your code, they don't know about all your dependencies. So if you just had manually installed your dependencies using pip install and didn't record that information anywhere, then that information is lost and they don't know about it. You would have to tell them, oh, hey, you need these dependencies to make this code work, or maybe they would even have to figure that out for themselves when they try to run your code and they got a bunch of errors about, oh, hey, request doesn't exist. But with Poetry and build tools, we can record this information. So this information is all logged in a file that you have checked into your repository. So when they check out your code from GitHub and they run Poetry install, it will automatically create a virtual environment and install all of the dependencies that your code depends on. This is going to happen when you fork the Learn Python repository and install it on your system. I already have a bunch of dependencies in there that we're going to be using, and this is just going to make your life a lot easier. It also does things like give us an easy way to build, like create the zip file or wheel file, as they're called, for our project. And this would be the file that we would actually upload to PyPy, and then we could actually upload it to PyPy using the publish command. The last thing to know about Poetry, and there are a bunch of different commands Poetry gives us, but one of the most important one is run. So recall, Poetry created a virtual environment for us. This is just a directory, right? And anytime we want to run a command, whether that be a Python command or something else that is going to use our virtual environment, we need to prefix that command with Poetry run. So this is just saying, run this in our virtual environment, whatever this command is. So our lessons are going to have what I'm calling gateway exercises. So at the end of each module, there will be like a little assignment, coding assignment that I'm calling a gateway because I don't want you to proceed past that module until you have successfully completed that gateway assignment. It's a gateway to the rest of the course. And we're going to use a testing library to test your gateway assignments. We're going to use a very popular testing library called PyTest, and this is a package on PyPy. You can go pip install it. What is testing? Well, in code, you're constantly updating code, and frequently you might break existing code when you update it. And so if you have a bunch of tests written that exercise specific parts of that code from the past, you can run that on your updates to make sure you didn't break anything. And I mean, for most like data processing or like just one-off sort of Python scripting projects, maybe it doesn't really make sense to write a bunch of tests for it. But if there's something that you think you might build on and use in the future, it can make a lot of sense to write even just like a few tests that exercise large parts of the system. And then PyTest is a library. It just provides us some tooling to make it easier to write tests. So we have to write less code to write our tests. Okay. So the next thing we're going to use, you could just program in a text editor, like TextEdit on OS X. That would be totally fine. But we live in the future now. And we have these things called integrated development environments, or IDEs. And these are just fancy text editors that have a bunch of additional features that know that the task we're doing is writing code, and these features help us write code better, faster. There are two main ones out there that people use for Python. There's VS Code, which is a Microsoft product, and then there's PyCharm, which is a JetBrains product. PyCharm is probably still has the edge a little bit in terms of all the bells and whistles it has, but VS Code is quickly catching up, and it's a much more modular design. So most of the functionality in it is installed via add-ons. So you only install the add-ons that you want, and it kind of keeps it smaller. Like I've noticed PyCharm tends to use a ton of my system resources, but I haven't used VS Code so much, but we're going to use it for this class, so I'm going to be learning it with you. VS Code has, as I said, it's an add-on model, so when you install it, you'll have to install extensions for Python, and those extensions are listed in the README, so please, when you install VS Code, go install all those. So, IDEs can provide a lot of different things for you. I don't tend to even use most of them, but some of the features I definitely use a lot of are, it can autocomplete. It has suggestions as you're writing. It can auto-suggest things. It can highlight things as you're writing codes that isn't going to run. And then it has easy sort of hotkey navigation, so you can jump around to different parts of the code easily to find what you're looking for. The last tool that we might use is AI. And I am not going to tell you not to use it. I think actually when used right, it has a place in learning how to program. And the way I think about this is in the difference between good struggle and bad struggle. When you're struggling, when you're in good struggle, the work that you are doing, the struggle you're doing is training your own neural network. It's building connections in your brain that you're going to need in the future to be good at programming. But you can fall over into bad struggle, and bad struggle is just you're wasting time. Like you're stuck on some problem. If you just had the right the solution to the problem requires information that you just don't have in your brain. If you find yourself in bad struggle, please, by all means, go ask ChatGPT a question. In the early modules, when you're learning the basics, I would not ask it to write your assignments for you. There are just some parts of the language that you just need to kind of get down and sort of struggle through, especially looping and those sorts of things. And in later modules, where the tasks are more complex, like plotting, for example, I never just sit down and write code that plots data anymore. My first thing is I go to ChatGPT and I say, give me a program that generates a plot that looks like this, and then I'll take that code that it spits out and I will edit it to fine tune it to what I want, and that is totally legit. if these tools can make our lives easier and we can program faster with them, we should. It's not cheating, it's just progress. I might try first, though, to do Googling, just so you can kind of get the feel of the difference between Googling programming questions versus ChatGPT. Maybe you try the same question in both and see which one works better. In my experience, ChatGPT will often be faster to an explanation, but sometimes deeper problems, it doesn't actually get you what you're looking for, and so you'll have to fall back to Google and dig through documentation or websites like Stack Overflow. So just get acquainted with the different modalities of search involved in this work, and it'll serve you. I promise the amount of PowerPoint we're going to be looking at is going to get better from here on out. So this is the interactive part. We're going to go fork our Learn Python on GitHub, and then clone it into VS Code and set up Poetry. So this assumes that you have Python installed on your system, that you have VS Code installed on your system, that you have Git installed on your system, that you have Poetry installed on your system, and that you have created a GitHub account. If you haven't done any of those things, go do them now. There are links to the installation guides are listed in the README. There are ample resources all over the internet that help you install those things. Okay, so this link I'll paste in the bottom at the bottom of the video, but this is the repository that Learn Python has created, so let's just click that. Okay, on GitHub, you're going to see this fork button. So first off, this is the GitHub view of the project. There's sort of a directory tree here that's navigable. We can go in and actually see the files that are part of the project. But the main part of the project is we have this README down here, this file, readme.md. This is rendered, and this is where there's going to be this is still in development. There's going to be some more information here. These are the prerequisites that you need to install, and these extensions are listed for VS Code, so please install these. Okay, so we are going to fork this project, meaning we're going to make a copy of this project to our own GitHub account. So just do that. Call it the same thing. Okay. Now you notice this is on our username. We have our own copy of this project now. If there are changes to what's called the upstream version, so the original repository, that's the one on my main account, and you need to pull those in, you can use this sync fork feature here. You can see right now it's not behind upstream. Okay, so now we're going to go look at VS Code. Let's copy this URL. We're going to go to Visual Studio, and we're going to say clone Git repository. All right, and then we need to choose a directory to put it in. And I just have a directory called development in my home directory where I do all my coding. Select this is where we want to download to. Okay. So there are lots of explainers and tutorials about VS Code out there. I'm not going to go into it in much detail, but we just have we have cloned this repository. All the files that are part of it are now on our local machine. We can navigate them through here. So all the preamble materials are in the preamble directory. The keynote presentation is in there. And then each of the modules are going to be in these module directories. So module 1 is the only one that's done right now. The keynote presentation that I'm working off of is in here under the resources directory. There's also some of the diagrams that are part of the presentation that are there, so you can see them more clearly. Okay. So now let's set up poetry. Well, first let's look at this PyProject.toml. So this is our poetry configuration. There's not a whole lot in here. We just have a name, current version number, description, author, license, README, packages pointing to this directory. We do have some dependencies already listed though. So this is saying this project requires Python 3.9 or higher. It depends on this thing called IPython that we'll talk about. PyTest we already talked about. And then this other thing called IPDB that we'll talk about. Okay, so VS Code comes with a terminal window. So this is just like the terminal app on your laptop. It can just be kind of convenient to be able to have access to it within the editor. So, I assume you already have Poetry installed. So just to check to see if you do and that it works, you can type poetry -- version. And it should spit out something that looks like this. Now, the first thing we want to do is run poetry install. And that is going to do two things for us. It's going to create a virtual environment for us to run our project in. And it is going to install all of these dependencies in that environment for us. Now, by default, Poetry is going to put that virtual environment into some cache directory somewhere else, but in general, it's sort of a better practice to have it create the virtual environment with your project. So we're just going to configure Poetry to do that for us, and you can see a list of Poetry configuration directives, and the one we are after is this one. So type poetry config, give it that value, space true, and that should set it to true. You should see this line now. Now go ahead and run poetry install. We'll see it added this .venv directory here and installed all of these packages off of PyPy. So if we look in our virtual environment here in the lib directory, we can see it dumped all of those packages into here. And we can import them. They should be accessible from our code base. Now VS Code should kind of automatically pick up that you have a virtual environment and configure itself to use it. If it doesn't, it might prompt you with a question like, oh, use this virtual environment, say yes. That just means when you're looking at code in VS Code, it's going to be running the Python interpreter in the backend, and you want it to be running the one from your virtual environment because it's going to have all of your dependencies and stuff in it. Okay, so the way this is structured is, I mean, the preamble materials are in preamble. The tests are going to check your gateway activities, and then the different lessons are going to be in these module directories. So the first one is in module. The resources for this module, like the presentation we just went through, is in here. Some images. but let's just briefly run through how Git works. So I'm in the main directory here. I'm just gonna create, let's see, I'm just gonna create a new file. Let's call it test.py. Okay, we can see VS Code says made this file. It's green. It's got this little update thing here. It says it's untracked. This just means this is a new file. We have not added it to Git yet. This little icon, this is the Git pane. VS Code integrates with Git, so everything you can do with Git on the command line, most of that stuff, there's some graphical way to do it through VS Code. You can also come down here into the terminal and use Git. So you can say git status. This says, oh, we have added this file, and Git doesn't know about it. We can add this file, means stage it for commit, either on the command line or by using the UI here. So let's just go ahead and add that file. So if we do status now, we can see, oh, these changes will be committed. And we can hit the commit button. Git is going to want you to add a comment to your commit. So this just says, you know, this is for just for the logs. So when someone is trying to figure out what your commit did, they can go and look at the log for the commit, and hopefully you've written a nice descriptive message. Test adding a file to show how Git works. And we'll accept that comment. And now, if we do status, we'll see there's nothing to commit, so our working tree is clean, but it says your branch is ahead of origin main by 1 commit. So origin main here is a repository on GitHub. The commit we just made did not get pushed to the internet. It just has been made locally. To push that back to our origin repository, we need to run git push. We can either do git push here in the command line, or we can hit this push button here. Let's go ahead and do that. You say OK. All right, so now when we do git status, it should say branch is up to date with origin main. All right, so we've added this file. Now, if we go to our GitHub repository, we should see this file now, and we do. And we can see that our branch is 1 commit ahead of BC Kohan main. We can go and we can see the latest commit. We can go and look at that commit. Okay, added a file. Okay. Let's go ahead and we can also remove files. We'll just do this on the command line this time. Git remove test, git status, all right, git commit, removed that test file, git push. All right, now if we put this, you can see it's not there anymore. And we're 2 commits ahead of where we forked. Okay, so after about 2 hours of Keynote, we're finally going to write some code. Just a little bit more Keynote before we get there. We just need to go over a few basic language constructs in Python, and then how we organize code on the file system and how Python finds that code. So when we import code, it knows how to import it. Okay, so variables. If you've used a language like Java or C++, a compiled language, those languages are what's called strongly typed, meaning when you declare a variable to exist in memory, you have to tell the compiler what type that variable is, whether or not it's an integer or a decimal number or a string of characters. And that's so the compiler knows how much memory space to reserve for it. And then you can never assign anything of a different type to that variable. Python, since Python has this extra layer of abstraction and has this interpreter that's executing bytecode, it does a bunch of extra work so that it doesn't have this constraint on your variables. You do not have to tell it what type your variables are, and you can reassign other types to a variable. So this is what that looks like. There are three variables here. We're assigning my integer to 1. We're assigning my float to 1.0, so a decimal number. This is also called a floating point number. And we're assigning my underscore string to a string of characters. And because we're loosely typed, I could then say my integer equals my string, and then my integer would contain the value of my string. That is totally fine in Python. If you've used a language like Java or C++, this naming might look a little weird to you. That's because by convention in a lot of languages, they use something called camel case, where the first word in your variable name is lowercased and every subsequent word is capitalized. And there's no reason for this other than people think it makes the code more reasonable. So it's just purely by convention. You don't have to do it. In Python, that convention is something called snake case. And that is, the words are all lowercase and they are separated by an underscore. So basic logic flow, all languages have something called if-else conditions. And that's just saying you can evaluate a condition to whether it's true or false and then execute code depending on whether it's true or false. So here we have a very basic Python if-else clause. There are three main switches, logic switches in Python. There's if, there's elif, which stands for else if, meaning if this first condition is not true and this next condition is true, we're going to do this. And then there's else, meaning none of the above conditions were true. So we have two variables here, my variable and my other variable. So our first condition says, if my variable equals my other variable, meaning the values are the same. So you notice when we assigned variables on the previous slide, we used a single equals, that's assignment. When we're comparing two things, we're going to use equal. And there are a bunch of other logical operators that we'll have a table of at some point. So this just says if my variable is the same value as my other variable, we're going to do whatever is indented below this if condition. So in languages like Java, they use curly braces to encapsulate blocks of code. But in Python, we use white space and indents in particular. So anything indented below this if condition is going to be executed if this condition is true. So if these two things are equal, we're going to print to the terminal. This is how we print to the terminal in Python. We just say print and then pass it a string. My variable is equal to my other variable. If this is not true, my variable is not equal to my other variable, Python will move to the second elif condition, and it'll say, if my variable is true. And now in Python, you can ask it to evaluate any variable to be a what's called a Boolean condition. That means whether it's true or false. And basically, if the variable is anything other than 0 or null, it's going to evaluate to true. So this is basically saying if my variable is not equal to my other variable and it is anything other than 0 or null, we're going to print my variable is true and not equal to my other variable. If neither of these two conditions is true, it moves to the else condition and we say my variable is false and not equal to my other variable. Okay, functions. Every language has the concept of a subroutine. They might be called slightly different things in different languages. In Python, the terminology is functions, so subroutines are called functions. In Java, you might be familiar with the term method. But a subroutine is just a block of code that you can call many times from many different places in your code. So why do we do this? Well, there's this concept called DRY. It stands for don't repeat yourself. And that just means code is going to be smaller, more easy to maintain, and less buggy if we duplicate code as least amount as we can. So, functions, they in all languages, they can take 0 to many arguments or parameters, meaning we can pass variables into them and they can work on those variables. And then they also have the option to return a value to the calling code. So in Python, when we define a function, since we're loosely typed, we don't have to tell the compiler what its return type is. The first thing in a Python function definition is this 3 characters DEF. And this stands for define. And it just says we are going to define this name to be a function. So we're defining a function called multiply, and it takes 2 arguments, number 1 and number 2. And then it returns number 1 times number 2 to whoever called it. And so down here we have an example of what it looks like to call the function multiply. So we are declaring a variable called result1, and we are going to assign it to the return value of multiply, where we pass the number 1 and the number 2 into it. So 1 here becomes the number 1 argument, and 2 here becomes the number 2 argument. And then result 2, we assign to the return value of multiply, where we pass in 3 and 4. So result 1 is going to, after this code executes, is going to equal 1 times 2, or 2. And result 2 is going to equal 3 times 4, which is 12. The other thing to note here is I have these lines after multiply with these little hash marks. This is how we do comments in Python. So anytime you see a hash mark, anything after this hash mark on the same line is going to be ignored by the Python interpreter. This is solely for us humans. As we're reading this code, we can add a little descriptive bit of information that can help whoever's reading the code interpret that code, like what it's doing. So in Python, we have these hash marks to denote single line comments. And anything on the same line after this hash mark is going to be ignored. Okay. How is Python organized on the file system? So you may have noticed already that Python code is put in text files that have the .py extension. And complex programs can be, they're organized in many different files. Some simple programs might just be one file of Python code. That's totally fine. But the more complex your program gets, the more work it has to do, the more files you're going to want to create. Software engineering is, I have this line here, software engineering is 30% art, 20% science, and 50% organizing. It really is a lot about organizing, and that's just because these code bases get enormous and they're hard to keep track of, and it needs to be easy to find what you're looking for. And there's an art to organizing. It's not unlike how you might organize your apartment. It is a subjective process. Different people are going to have different opinions. There's often no right way. And if there's any rule of thumb, it's that you put like with like. So if there are certain parts of the code that are all involved with doing a particular task, you might put those in the same file or the same module. But really, it is personal preference, and it is informed mostly just by having done it before and coming up with patterns that work for you, or seeing patterns that other people have used and sort of using those patterns. But there's no right or wrong way necessarily. So in Python, there are three concepts to understand about how we organize code into multiple files. There are Python packages and modules, import statements, and something called the Python path. And we're going to go through each one of these. So, packages and modules. I have here on the left an example directory tree. This is kind of this. If you look at our Learn Python repository, it's not going to look exactly like this. I've kind of removed some things and it's a little old, but let's just walk down this. So python.py files are referred to as modules. Directories that have this special file called __init__.py are called packages. So if we look here, we have a package, which is this directory learn Python, because it's got this init Python file. We have another package that is confusingly called module1 that has this __init package. We have this other package called tests that has this init file. So we have a package that has learn Python, another package module, another package test, and then we have a bunch of different modules here. So we have a utils module in the learn Python package, and we have hello world module in the module1 package. It's not by accident that I named this package module. It's because there's a lot of what's called terminology overloading that you will find in software where the same word is used to mean multiple things. So in this context, from the context of our lesson, this is a module in the lesson. But when we look at it in the code, it is a Python package. Okay, so when Python, let's say you have a function that you have defined in hello world.py in this module, and it's called myFunction, and it multiplies two numbers together. Say you want to call that function, invoke it from your module test.py in the tests package. We're going to use something called dot notation to do that. And dot notation is just like a directory path or a file path. We're just going to replace the slash with a dot. So in Python, we have import statements, and this is what they look like. So these are two different ways here that I'm showing of how you might import this function from hello world module. The first one, we're just going to import this top level package. So from test.py, we can import the learn Python package. And then we can refer to anything that is in here by using its path and dot notation form. So we start at learn Python dot module1 right here, dot hello world, dot myFunction, which exists in hello world. And this is a call. We're going to invoke it. A better way to import code is to use a from import statement. So this just says from, and we're going to pass it learn Python module1 hello world, import myFunction from hello world. And then in code, we don't have to prefix it with its full path. We can just use its name directly. Okay. The last thing is the Python path. So if we go back here, when we do this import statement, this is a directory on our file system somewhere, this learn Python. Python needs to know about that directory to be able to execute this import statement. And the way it knows about that directory is the Python path. The Python path just means it is a list of directories that the Python you are using is configured to search for code in. And so I just went in our virtual environment, in our repository here on my local machine, and I had it print the list of paths that are on my Python path. And you will notice that the last one here is our learn Python directory. That's how it would be able to find it. Execution flow. When a Python module is imported, so when we do this from learnpython.module.hello-world import my function, at this point in time, all of the code in this hello world module file is executed. Now, if we don't have any calls to my function in that hello world, at no point is this function going to be evaluated. Like it's not going to actually, do a number one times number two anywhere. Like what it means when a function definition is executed is simply that this function is defined in memory now and we can invoke it. Sometimes you don't want to execute code when your module is imported. An example of this might be a script that you might want to invoke as an executable on the command line. For example, you want to run it, you want to say my python /myscript.py. Like that is your entry point into running code. But some other code somewhere might import your MyScript module and use functions that you have defined in there. And when that happens, maybe there's some execution flow that you don't want to happen when someone imports it, but you only want to happen when someone invokes your script as an executable to run. In that case, Python sets this special variable called __name to equal the string main. So whenever you invoke a script like this condition is going to evaluate to true. So this is just by convention. Anytime you write some Python code that you're going to want to call, as an executable script, this would be your entry point, and you would start, executing your code here. We have this keyword called pass here. In Python, this basically just means do nothing. So this is analogous, if you've used Java, to the main function. Public static void main, blah, 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 blah. You can think of it like that if you've used Java. Now, we've seen a couple examples now of these __ names that are special in Python. Like we had our __ init files in Python. And now we see __ name. So what's going on here? There are a number of special variable names and file names that Python reserves and sets for you. They're just sort of like useful things that you might need. And by convention, Python uses the __ as a prefix and suffix to the variable, mostly as a way to deconflict them from words that you might want to use as variable names in your own code. Like, for example, name here is a very common name that you might want to use for your variable name. So Python didn't want to take that away from you and say that, oh, we're going to use it. So it sort of, anytime you see a a double underscore, which are called dunder for short names in Python. Those are probably special variables that the language is going to set for you. And there's quite a few of them, and they're documented in the standard library, and we'll see more of them later. So, since Python is interpreted, we actually can write code and have that code executed in an interactive way. Since we don't have this extra compilation step, if we just type Python from the command line, a live interpreter will open, and our Learn Python package also installs with a more user-friendly interpreter called IPython, which stands for Interactive Python. And so let's just look and see what that looks like. So I'm going to open Visual Studio or VS Code here. All right, if I just type Python, you'll see that if you type Python without passing in an executable file, it just opens the interpreter. And this, I can type Python code into this, and it will be evaluated. So on the last slide, we looked at our Python path. This is how I did that. I just said import sys. This is a module that or a package that our standard library provides. And there is a attribute on the sys module called path. And if we look at it, we see we have this list, and it's just a list of paths. And there's another Python module called pprint, which stands for pretty print, which will give me a more user-friendly version of that path. So there we go. So you notice when I invoked Python here, I just typed Python on my terminal. And you'll see it doesn't actually have Learn Python in the path. So if I tried to import, let's try to import test. It's going to tell me it can't. Well, it can because one of the paths that are on syspath is always the current directory. So if I were to exit out of our terminal, which you can do by typing exit or Control D, let me move up a directory. Let me start this again. If I do import learn python.tests, it's going to say no module not found error, no module name learn Python. So recall that Poetry is doing a lot of work for us. It's setting up a virtual environment, and when we call Poetry run, it's going to make sure that we're using that virtual environment. So there is a command on terminal called which that'll give you the path of the executable it would use. So if I say which Python, it's going to tell me which Python it's actually going to use, and we'll see that this is a Python that is n.pyenv. But if I do Poetry run which Python, we can see that it's going to use the Python from our virtual environment that Poetry has created. So if I do Poetry run Python and import sys, and let's look at our path, we'll see that it has added both two things to the end of our path. It has added our Learn Python directory, and it has added the site packages of our virtual environment here. So this is any of our dependencies are installed here, and that's how it's going to be able to find them. Now recall that if you look at our TOML file, we have a dependency on IPython, this interactive Python interpreter. And so it was installed into site packages. So if I do Poetry run IPython, you'll see that it's similar, but it's a little bit different. So if it's got some autocompletes, but if we import sys here, and let's say sys.path. You see it kind of automatically pretty prints it for us. I didn't have to invoke that function. So IPython is just a more sort of user-friendly, interactive Python terminal. And I actually use the interactive terminals quite a bit, especially if I'm checking to see if how some function works, or if something will evaluate. I might just pop open a interactive terminal and just check it out real quick. Okay, let's go back to Keynote. It is time to write your first Python program. So this is Gateway Exercise 1, and we're going to split this into 2 parts. In this first part, I want you to create a Python module called Gateway 1, and I want you to put it in the module 1 package. And I want this to print these 3 statements to the terminal when you import it. All right. So like when you open a Python terminal and you import learnpython.module1.gateway1, you should see this output. To test that your Gateway 1 code is passing, we're going to use PyTest, and this is how you're going to invoke it. You're going to say poetry run PyTest -k and give it this name, test underscore gateway 1 underscore part 1. That is going to run a test that I have implemented in Learn Python tests test.py module that will check to make sure that what I am expecting has happened. All right. After that's passing, I want you to go to part 2. And in part 2, the first behavior should remain the same. So like when you import Gateway 1, it should still print 1, print 2, print 3. But I want you to modify it so that when you invoke the Gateway 1 module as an executable using Python, learn Python module 1 gateway1.py, I want it to print 1 and print 3 like it was the first time, except for now, instead of printing 2, I want it to print hello world. Python will look for code in these directories. So, and then I want you to pretty print the Python path. Okay, and then to test that, you can test both of them, that both of them are still working. Just run poetry run pytest-k test underscore gateway 1. All right, and that's it. And once you have that passing, feel free to go to module 2, where we're going to get a lot more into the code.